Well students, this is another application of Gauss law to find the electric field due to a uniformly charged thin spherical cell. You have learnt about the electric field due to a linear charge distribution and the electric field due to a plane sheet of charge. In this video, let's find the electric field due to a uniformly charged thin spherical cell. Let's consider a spherical cell of radius r. Charge q is given to this spherical cell. So the charge q resides on the surface of the spherical cell. Q charge plus q charge. Again, it is a surface charge distribution and sigma is the surface charge density. It is the surface charge density. Sigma is equal to total charge on the surface divided by surface area of this sphere. It is q by 4 pi r square. Let it be the equation 1. Now let's find the electric field at a point outside the spherical cell. Let this point P. At point P, you want to find the electric field due to this spherical cell. To find the electric field at this point, which is at a distance r smaller from the center, let's consider a spherical Gaussian surface of radius small r. This spherical charge distribution is symmetric about this Gaussian surface. The field line due to this spherical shell, charged spherical cell, it is outwards like this, radially outwards. Now let's consider small element ds here, area vector. The electric field and area vector, they are in the same direction. At each point you will find area vector and the electric field, they are in the same direction. So to find the net flux passing through this surface, that means we have to find integration of E dot ds over this spherical Gaussian surface is equal to E and ds are in same direction. It means it is E ds cos 0 degree. That is equal to integration of E ds cos 0 is 1. Now the electric field at each point on the Gaussian surface is constant since it is symmetrical about the charge distribution. So this E can be taken outside. It is integration of ds over this spherical Gaussian surface. Its radius is smaller. So what is the surface area of this Gaussian surface? It is 4 pi r square. That is equal to E into 4 pi small r square. This is integration of E dot ds. Let this be the equation 2. Now what is the charge enclosed by the Gaussian surface? Is the total charge q. Q is enclosed by the Gaussian surface. So charge enclosed, q enclosed is equal to, you can write q, or that is equal to sigma a. That is sigma into a. If we put the value here, it is sigma into what is the area of this spherical cell? It is 4 pi r square. So this is the charge enclosed, equation 3. You got integration E ds over the Gaussian surface, closed surface. You got the charge enclosed by the Gaussian surface. Now you can apply Gauss law to find the electric field at the distance r. According to Gauss theorem, it is integration of E dot ds over the closed surface is equal to charge enclosed by the closed surface divided by epsilon naught. Now you put the values. Substituting the values, integration of E dot ds from equation 2 and charge enclosed from equation 3, it is E into 4 pi r square is equal to sigma into 4 pi capital R square, this is the charge enclosed, divided by epsilon naught. Your 4 pi cancelled. What is the value of E? It is sigma into capital R square divided by epsilon naught into small r square. This is the electric field outside the spherical shell at a distance r from the center of the spherical shell. This is the final expression for the electric field outside. If the value of sigma is put here, then you will get an expression in terms of Q also. Now putting the value of sigma from equation 1, sigma is the surface charge density. Now putting the value from equation 1 using equation 1, it is E outside is equal to sigma. Sigma means the value of sigma you have to put here. The value of sigma is Q by 4 pi r square into capital R square divided by epsilon naught into small r square. The value of sigma is put here. This cancelled. It is Q by 4 pi epsilon naught r square. So E outside is exactly similar to the expression as if the total charge Q is concentrated at the center of the spherical shell. This is the electric field due to a point charge. So we got the expression exactly similar to the electric field due to a point charge. That means as if the total charge is concentrated at the center of the spherical shell. Now let's find the electric field at a point inside the spherical shell, which lies inside the spherical shell, and its distance from the center of the spherical shell, let it be r dash. So you have to consider a Gaussian surface of radius r dash. It is spherical Gaussian surface. So let's find E inside. It is case 2. E inside. And first one, it is case 1, E outside. Okay. Again, what is the charge enclosed by this Gaussian surface? A charge enclosed, Q enclosed is equal to 0, because all the charges, they reside on the surface of the spherical shell. So no charge is enclosed by this smaller spherical Gaussian surface. So Q enclosed is equal to 0. Again, integration of E dot ds over this spherical Gaussian surface is equal to E into 4 pi r dash square. If Gauss law is used, we have integration of E dot ds is equal to Q enclosed by epsilon naught. This implies E into 4 pi r dash square is equal to 0, because Q enclosed is equal to 0. Since 4 pi r dash square, it is the area, it cannot be 0. So this implies E is equal to 0. That means E inside the spherical shell is equal to 0. So inside the spherical shell at every point E is equal to 0. and outside the value is equal to sigma capital R square by epsilon naught small r square. Using this formula, you can find what is the electric field on the surface of this spherical shell. If you want to find the electric field on the surface, that means the Gaussian surface is of radius capital R again. That means small r is equal to capital R. If small r is equal to capital R, then E on the surface is equal to sigma by epsilon naught. So let's see case 3. Let's see case 3. On the surface, E on the surface of the spherical shell. So here small r is equal to capital R. That means if you want to find the electric field here, you have to consider a Gaussian surface of radius capital R. Substituting the value in equation 4, putting in equation 4, so E on the surface is equal to, it is sigma by epsilon naught r square by r square. So it is sigma by epsilon naught into capital R square divided by capital R square, small r is capital R. So you will get it is sigma by epsilon naught. So E on the surface is equal to sigma by epsilon naught. Let this be your equation 5. So let's summarize it. Due to this spherical shell, the electric field inside is 0. Suddenly the value on the surface is maximum, is sigma by epsilon naught. If we will move away, then the value of the electric field decreases. In this expression, E outside proportional to 1 by r square. So it decreases with increase in distance. If a graph is plotted between the electric field and the distance from the center of the spherical shell, you will find the graph. Electric field is taken along y-axis and the distance from the center of the spherical shell, it is taken along x-axis. From the center we are moving. At the center electric field is 0. It's 0 up to the surface. Means it is 0 up to the surface. That means up to capital R. Suddenly at capital R, the electric field becomes sigma by epsilon naught. This value is sigma by epsilon naught. Then if we will go further, the distance increases, the electric field is proportional to 1 by r square. So outside E proportional to 1 by r square. This is from the center O up to the radius E is equal to 0. Suddenly it increases, the value becomes sigma by epsilon naught on the surface, then it decreases with increase in distance, E proportional to 1 by r square outside. So this is all about the electric field due to a uniformly charged thin spherical shell. Thank you.